Fuels sourced from hydrocarbons currently account for over 80% of global energy consumption, and in spite of the advent of greener alternatives, this statistic is unlikely to change significantly in forthcoming decades. Indeed, by 2030, reliable projections suggest that the world will be consuming just under 105 million barrels of oil per day and around 460 billion cubic feet of gas per day. By 2030, the world will require approximately 35% more total energy than at present. In 2010, 60% of crude oil production was classed as sour or medium sour on the basis that it contained significant levels of elemental sulfur, and according to the International Energy Association, the IEA, 70% of known crude oil reserves and 40% of equivalent natural gas reservoirs now contain a high content of sulfur, sulfurous compounds, and carbon dioxide. It follows, therefore, that future projects which use high-strength pipelines to deliver such hydrocarbon resources to refineries and other processing plants will face increasing engineering issues. So what exactly are sour hydrocarbons? Crude oil is considered to be sour if its total sulfur level is above 0.5% and sweet if below this figure. Sour gas must also contain sulfur, often in the form of hydrogen sulfide, and by definition, levels of greater than 4 parts per million are required to warrant such a classification. However, in both oil and gas, hydrogen sulfide may be present in conjunction with significant moisture, and this combination, either alone or exacerbated by the presence of carbon dioxide, can produce severely corrosive environments which can rapidly attack line pipe steels in very distinctive and dramatic ways. In fact, more than 13% of known gas reserves are severely sour and contain more than 10% of hydrogen sulfide, and more than a quarter contain more than 10% of carbon dioxide. These acidic gas mixtures present major challenges for materials scientists and pipeline designers. Mechanistically, it's the diffusion of molecular hydrogen through the steel to susceptible microstructural features which inflicts the damage, and as we will learn later, the secret to effective control of this problem derives from the application of fundamental metallurgical knowledge in a rather unconventional and unexpected way. This is a complex subject, but it has been clear for many years that higher levels of the element manganese, which is beneficial to steel strength, can, because of the way in which it segregates during continuous casting, end up being specifically detrimental to the ability of a steel to resist sour surface attack. Unfortunately, manganese combines with sulfur and produces elongated sulfide inclusions in the rolled product that are largely responsible for the initiation of many of the cracking mechanisms encountered when steels are exposed to sour environments. The conventional approach to the problem is not to interfere with the steel's overall metallurgical blueprint, but to reduce the steel's sulfur and other impurities to the lowest levels practicably achievable, and to employ calcium treatment to radically alter the shape of the resulting inclusions. The specific action required depends on the severity of the exposure conditions. Many years previously, rare earth elements such as cerium were used to similar, though less reliable, effect. Historically, carbon and manganese are the building block elements from which ferritic linepipe steel strength is derived. Whilst the quest for improved weldability has progressively driven carbon to much lower levels, in recent decades, to conceive of an alloying strategy with dramatically reduced manganese levels would generally be considered to be an impractical proposition. Indeed, it would be fair to say that the use of manganese to cheaply and readily improve steel strength is entrenched in global steelmakers' thinking. However, resurrecting an idea which he developed, nurtured and patented decades ago, Dr. Malcolm Gray of the Microalloyed Steel Institute, based in Houston, Texas, surprised attendees at a 2012 CBMM sour gas seminar in Sao Paulo with his original and lateral thinking by proposing much lower manganese steels for sour gas service. As suggested earlier, The higher the manganese in the steel, the more prospect there is for peak concentrations to build up in the centerline region. In essence, Dr. Gray's impeccable logic suggested to him that if manganese is the problem, take it out and replace it with alternative strengthening elements. Since niobium is the key microalloying element which features in the overwhelming majority of progressive metallurgical designs for thermomechanically rolled high-strength linepipe steels, it is perhaps not surprising that Dr. Gray opted to utilize this element's powerful effect on steel transformation in conjunction with chromium as a replacement for manganese. Effectively, 1% of manganese can be replaced by 0.08% of niobium. Rather surprisingly, the efficacy of this mechanism in low-carbon steels is still not widely appreciated. The reduction in manganese below 0.5% reduces continuous casting segregation dramatically. What could be simpler? It is, of course, rather more complicated, and the metallurgical manipulations required to make a success of this novel strategy could not have been deduced without the detailed knowledge and experience of a metallurgist of Dr. Gray's caliber. Dr. Gray's 2012 presentation was sufficiently authoritative and convincing to persuade CBMM to sponsor and coordinate a remarkable international project to evaluate the commercial potential of the new alloy development. More importantly, key steel makers and pipe manufacturers were also persuaded, and some 2,000 tons of steel were produced in Mexico, China and Germany, and subsequently processed in 11 countries and 27 different steel processing and pipe manufacturers. A truly remarkable international collaborative project. Some aspects of the project are ongoing in certain countries, but enough data had already been gathered by the autumn of 2014 to merit an opportunity for all participants to share their results and experiences from this worldwide trial. In consequence, early in September 2014, Companhia Brasileira de Metalurgia e Mineração, CBMM, hosted a further unique and important international seminar in the fascinating city of São Paulo, Brazil. The event, entitled Ultra Sour Service Low Manganese Linepipe Steel, The New Paradigm, was held in the magnificent setting of the new headquarters of the Associação Brasileira de Metalurgia e Mineração, ABM. Initial results have been impressive, with strength and toughness levels exceeding the expected API 5L x65 range, along with enhanced immunity to severe sour service. The bulk of the data gathered to date has vindicated Dr. Gray's vision and methodology, and later, in an interview recorded during this seminar, we will hear in detail from him about the seminal metallurgical thinking behind his unique concept and the full history of its development, which culminated in the trials leading up to this important gathering. Prior to the technical program, the invited participants were welcomed to São Paulo at a special evening reception held on the 1st of September at the Hotel Caesar Business. And the seminar itself was held over the following 2 days. Introducing the seminar on day 1 at the ABM headquarters, Tadeu Carneiro, the Chief Executive Officer of CBMM, welcomed delegates and paid tribute to Dr. Gray's outstanding contribution to the overall CBMM worldwide technical development program, before focusing on the potential importance of this latest initiative. Tadeu also thanked other key participants and organizers for their roles in making this event a reality. Over the following day and a half, each invited organization openly presented their experiences with the new alloy compositions, and the presentations were interspersed with valuable and constructive technical discussion sessions chaired by carefully selected industry experts. At the conclusion of the event, on behalf of CBMM, Dr. Frank Barbaro of Barbaro Associates of Wollongong, Australia, summarised the principal findings of the work completed to date. He reminded delegates of the key technical features of the development and set out the areas where future clarification and additional data would assist in the adoption of the new technology by suppliers and end users. There is still much to learn, but there is already no doubt that this seminar will act as a stimulus for leading steelmakers and their clients around the world. The technology is openly available and everyone has the opportunity to benefit from its application. We can confidently look forward to seeing Dr. Gray's vision bearing commercial fruit to the advantage of both the supply chain and end users. We will now hear directly from some of the key speakers and participants, including Dr. Malcolm Gray, who have contributed to the undoubted success of this remarkable venture and this unique video record. You can also view an extended interview with Dr. Malcolm Gray, who will recount the remarkable story of this new development from initial concept to where we are today.
The seminar for the last 2 days brought together, I think, 26 different organizations who openly presented their results. I would say 90% of which were highly favorable and in terms of delivering the results that we had anticipated. Me in particular, since I'd already made quite a bit of steel according to this concept, and not necessarily made by very good steel makers. That with the 3 steel makers making these slabs, I always expected to get first-class results. Maybe the biggest surprise is that we got almost no poor results. We didn't totally explain how to roll this steel, how to coil it, how to make pipe, and all the details. We left that to the imagination of the participants. But within some broad, in a broad sense, we didn't have any undesirable results. One of the interesting things about this week's seminar has been the enthusiasm for the participants to identify other areas where this concept might serve some purpose, whether it's because they have poor casters or whether they have problems meeting toughness requirements with conventional metallurgy. The toughness of this steel is excellent and surprising a lot of people because of the low manganese content. But the PCM of this steel is around about 0.1 or 0.11%, which is half of PCMs you find in the structural arena for bridges and ships and pressure vessels and similar applications. So I'm expecting that there will be a diversification of the applications for this concept. In fact, Salzgitter already indicated that. The speakers from Jindal SAW in Houston, JSW, have already applied it for machinery bases to prevent centerline cracking. It's being considered for tank cars, railroad tank cars, and other structural applications where the ease of weldability is going to justify the use of this material, even if it may be slightly higher cost to manufacture.
Talking about this new concept of alloy, one thing that I observed during the seminar, that a very good hydrogen-induced stress crack resistance. All the value is 0. That is fantastic for us, because one of our limitation when select material for instance, for pre-salt gas pipeline is the HIC. Sometimes the company can reach our requirement. And I could see here that the HIC resistance is fantastic, because of this, I think this new concept will be very nice to have higher corrosion resistance, talking about HOS, of course.
It's a very interesting project because it gives us an opportunity to discuss globally a new idea, a very creative idea, to try to find a solution to produce steels with a higher resistance to in hydrogen induced crack. And up to now, we rolled all the slabs and evaluated the results at the hot coils with very, very good results. And we are very optimistic with this idea in order to solve this solution, because there is no one unique solution. You have to involve everybody in the world in order to find the best solution to this great issue. As I said, alone it's not possible to solve one problem. Then the idea of CBMM to involve everybody all over the world in order to discuss about this idea was great idea. It was a great project, and the level of the discussion is very high. And you can see up to now that with all the plants in the world involved, it's the best way to clarify all the options and then identify the best way to solve this issue in order to produce a more competitive steel for this kind of project with the hydrogen induced crack.
For the trial produce of non-manganese hydrogen pipeline steel, and depending on my experiences, I think this no manganese alloy design is very beneficial to reduce the centralized segregation for the continuous casting, and also very good for soil service, because this kind of steel have a very good HIC resistance and SCC resistance. So I think this steel is very useful for soil service. I would like to thank CBM, and have a long-term cooperation with the CBM. And I think after this seminar, we'll have further cooperation, and we'll have a good future.
First of all, I'm quite surprised, positively surprised about this high scientific level of this seminar. I enjoy it really. It's very important to see what the other people had done, and it's also interesting to see how the results are differing, how they are varying. It's a reason more to be here, also to meet new people.
I get involved in this project in the year of 2012. Actually, I'm from Shougang in China. Our factory is the first one who entered this project. Actually, in 2012, Mr. Gray made a visit to our group and gave us the information of this new concept. In our cooperation, we have already made mass production of pipeline steels for our service. So this project is very important to us, and we found it very interesting. So we did some experiment work, and also we did some industrial trials and investigations. We found it is valuable to use this concept in the production.